Hello and welcome to the course Introduction to R Programming. In this course, I will use RStudio as my integrated development environment or IDE. You can run your own R code the way that you prefer. If you need to install R and RStudio, then that is a standard procedure, and if you need any guidance, then just check out the internet and you will find what you need. In this course, we will first go through some slides to get an overview of R, and then we're going to look at some actual R code. So with that said, let's look at the course content. So we're going to begin with looking at what is R and RStudio. Then from 3 to 16, we're going to basically cover the fundamentals of R programming. Then we're going to look at some statistics and linear regression. And then we're going to look at a collection of packages that are called Tidyverse. More specifically, we're going to look at the packages Tibble, dplyr, and ggplot2. So when we have gone through the slides from 1 to 22, then we're going to have an actual code session in R. So with that said, we are ready to begin. What is R? R is a programming language for statistical computing and graphics. The name R stems from the language being a successor of the S programming language, and it is also the shared first letter of the founders Ross and Robert. If you would like to check out the official website of R, you can do so at this link. Here we see a picture of RStudio, which is an integrated development environment for R. So here we see some code in a script, and here at the console we can see command history and also results of executed code. In the environment you can see information about variables and datasets currently stored in the working environment during your R session. So for example, here I have created a variable called myMessage, and that variable, myMessage, we can see that here in the environment. Here at Packages, we can install packages through a graphical user interface if we prefer that, but as I will show later on, we can of course also install packages directly through code. And then here at Plots, we can see plots that we have created. And later on in the course, we're going to create several plots and they will be available to look at here. And then we can also go to Tools and go to Keyboard Shortcuts Help to, for instance, see how to execute code and comment code. So if I go to RStudio and then Tools, Keyboard Shortcuts Help, and scroll down to Execute, then we can, for instance, see how to run selected lines. And if I scroll up again to the section Source Editor, we can, for instance, see how to comment or uncomment lines, and for example, how to insert a section. So if I go back to my PowerPoint slides and to the next slide, here I have basically summarized what I just said. So check that out. When learning a new programming language, the first thing you often do is to print out the message "Hello World." In R, that is very easy to do. You simply type print and "Hello World." R can be extended through packages, and that is one of the reasons why R is as famous as it is. So here I will provide an example on how to install and load Tidyverse, and I'm using Tidyverse because we're going to talk about that later. If you would like to install and load another package, then you just change the name. So to install a package, we use the function install.packages and then specify the name, Tidyverse in our case. And then once you have installed the package, you can load it, and then you use the library function and specify the name of the package that you want to load, Tidyverse in our case. So you install the package and then you load it. If you would like to see which packages are currently loaded, then you can use the search function. If you would like to see packages relevant for different topics, then this link is a great resource. So if I press on this link, then we see that we have different topics such as econometrics, finance, and machine learning. And for instance, if I press machine learning, we see that, for example, we have different packages for random forests, which is a machine learning model. So this site contains packages related to different topics, so check it out and see if you can find something interesting. The standard approach to assign a variable in R is by using this arrow. This is called leftward assignment, and it is quite logical because this arrow here is pointing to the left. We can also do what is called rightward assignment, and in this case the arrow is pointing to the right. But rightward assignment is definitely not as common as leftward assignment. So this is what you will see all the times, and I personally have not seen this very often. You could assign a variable by using the equal sign, but that does not follow the style guide. And what we mean by a style guide, I will explain that in the next slides. But for now, you can just know that we can assign variables by using the equal sign, but in R you should not do that. If you would like to print out all the variables in the workspace, then you can use the function ls. A style guide provides consistency, making it easier to read but also to write code. There is no official R style manual, but by looking at how source code and/or documentation in R is written, we could sort of work out an implicit guide. So for example, if we run the following code in R, $mean, then we would display the documentation for the mean function, and if we read the documentation, we will see the following example. So in this example, we have not yet talked about vectors, but they are creating a vector and then assigning that vector to the variable x by using the arrow sign. So obviously, if the documentation is assigning variables by using the arrow sign, we should do the same. So we could work out an implicit guide for how to write our code, but in this course we're going to use the Tidyverse style guide, which is widely used by R programmers. This style guide is available at this link. And I definitely recommend you to read this style guide as soon as possible. Okay, let's go back to the slides. So I have written down some takeaways from the style guide, and the first one is use the arrow sign, not equal sign for assignment. If you load packages, do it at the very top of the program or the beginning of the program. In general, variable names should be nouns and function names should be verbs. And strive for names that are concise and meaningful, although this might sound easy, but in reality it is not. Variable and function names should only use lowercase letters, numbers, and underscores. Use underscores, also called snake case, to separate words within a name. If you want to break up files by chunks, then use the following commented line type. In code, use comments to explain the why, not the what or how. In data analysis code, use comments to write important findings and analysis decisions. If you need comments to explain what your code is doing, consider rewriting your code to be more clear. Styler is a package allowing you to interactively restyle selected text, files, or entire projects. It also includes an RStudio add-in, making it very easy to restyle existing code so that it conforms to the Tidyverse style guide. So at this link, you can check out the Styler package, and it is very easy to install. But I have also prepared an example in RStudio. So if we want to follow the style guide, we should use the arrow sign when assigning a value to a variable. But let's say that I write test equals sign 10. This does not follow the style guide, and if I select this code and then go to add-in and select style selection, then we will see that this equal sign will be transformed to an arrow sign. So I press style selection and we see that the equal sign was transformed to an arrow sign. So by using this add-in from Styler, it's really easy to follow the style guide. Finally, I would like to really emphasize that you should read this style guide as soon as possible, because it will make your programs better and more clear. R has 6 basic vector types: logical, integer, real, complex, string or character, and raw. Single numbers such as 4.2 and strings such as 4.2 are still vectors of length 1 in R. In the next slide, we're going to talk about data structures. Data structures are used to store data. The 6 basic data structures are vectors, which are one-dimensional collection of elements of the same data type, or in other words, homogeneous. Arrays are multidimensional and homogeneous. Matrices are two-dimensional arrays. So matrices are just a special case of arrays. Factors are used for storing categorical data, and lists are one-dimensional and heterogeneous, meaning that elements can be of different data types, and you can also store, for instance, vectors, matrices, and so on in a list. Dataframes are two-dimensional and used to store tabular data. The columns in a data frame can be of different data types. So these are the 6 basic data structures in R. In programming, an operator is a symbol used to perform some kind of operation. So in that sense, they are very similar to functions. So later on in the code, we're going to look at arithmetic operators such as addition, subtraction, and multiplication. We're also going to look at relational operators such as less than. And then we're also going to look at logical operators such as the logical and the logical or. In this example, I'm going to demonstrate the use of conditional logic. More specifically, I have created a program to check whether a number is considered low, medium, or high. So in this case, I've created a variable x and assigned the value 15 to it. If x is less than 10, then I'm going to print out the message low. Else if x is greater than or equal to 10, and x is smaller than or equal to 20, then I'm going to print out the message medium. Else, I'm going to print out the message high. So in this case, x has the value 15 assigned to it, meaning that it is between 10 and 20, and hence the message medium is going to be printed out. In this program, you can also notice that I'm using double ampersands, and if you're interested between the difference between a single and a double ampersand, then you can check out this link here on Stack Overflow. R has several built-in functions. Some examples include sum, max, min, and mean. So in this first example, I have created a vector containing the elements 1, 2, and 3. And we know that it is a vector because we use the function c, which stands for concatenate. So we have created a vector containing the elements 1, 2, and 3. Then I'm using the built-in function sum and providing this vector as its argument. So because 1 plus 2 is 3 and 3 plus 3 is 6, this function here with this vector as an argument is going to return the value 6. In the second example, I have created a variable called myString, and I have assigned the string "programming is great fun" to it. And in this string, you can notice that we have some mixing upper and lower cases. So if I use the function toUpper and provide the variable myString as an argument, then this function is going to return "programming is great fun" but in uppercase. In this example, I have created a function called rectangleInfo, and this function takes two arguments, length and width. So in the function, I define a variable called area, and area is equal to the length times the width. And then I define a variable called perimeter, and perimeter is 2 times the length plus the width. And then I create a named list, and in this named list I store two values, the area and the perimeter. So I store two values, which are the area and the perimeter. And then at the end of the function, I'm going to return this named list. So this is a function that returns multiple outputs. More specifically, it returns two outputs, the area and the perimeter. Once this function is created, I can call it in different ways. So I can call it by providing two positional arguments, in this case 2 and 2. I can also call it by using the default value for width. So in this case here, I only provide one argument, which is 5, and then I'm using the default argument for width, which is 4. And then here in the last example, I call the function by using keyword arguments, and I have also changed the order of the arguments. So now I have provided the width first and then the length. So as you can see, it's quite easy to create user-defined functions in R. In this example, I have created a list called languages, and this list contains different strings such as R, Python, MATLAB, and so on. Then I'm creating a for loop which says the following. So for language in languages, print language. So we have an iteration variable that we call language, and then for each language in languages, which is this list here, print out language. So what this for loop is going to do is that it's going to print out each separate string in this list. So it's going to print out R, Python, MATLAB, SAS, C, and so on. So this is a for loop. In the next example, I've created a while loop. And what I've done here is that first I've created a variable I that is equal to 0. And then I say while I is less than 4, print I. And then for each iteration, I increment I by 1. And if I didn't increment I in each iteration, then this while loop would continue forever because the condition I is less than 4 would always be true because I is 0. So it's important to increment I for each iteration, else this while loop will never end. In this example, I am storing values from a for loop in two different approaches. So in the first approach, I append an empty vector. More specifically, I create an empty vector called myResults. And then for I in 1 to 100,000, I create a variable called result, which is equal to I squared. And then for each iteration, I append my vector myResults by this code here. So as I said, the first approach appends an empty vector, and then the second approach is replacing elements in a pre-allocated vector. So what I do is I create a vector called myStorage, and I say that it is equal to integer 100,000. So what this code does is that myStorage will have 100,000 elements that are all 0 from the beginning. So myStorage will have 100,000 elements and they are all 0 from the beginning. And then in the loop for I in 1 to 100,000, once again, I create a variable result, which is equal to I squared. And then I say that the ith element in my storage is replaced by result, which is I squared. So this approach is replacing elements in a pre-allocated vector. And then for both of the approaches, I'm using the function system.time to measure how long this code takes to run. So I'm using system.time in this first approach and system.time in this second approach. And now the question is, which of these approaches do you think takes less time to run? So you can think about that and then try it out in the code later. You can load in many different data types into R, and in this example I'm demonstrating how to load Excel data into R. So to load Excel data, the first thing we do is that we install the package read_excel, and then once the package is installed, we load the package by using the library function. And when the package is loaded, we have a function called read_excel, and the argument that we provide to read_excel is the path to the Excel file. And in my case, I am storing the Excel data into a variable called myData. So as you can see, it's easy to read in Excel data into R. In this example, I've created a vector x containing a sequence of 10 values from -3 to 3. And then for each of the elements in x, I'm squaring it and storing the result in y. So y is simply the values in x squared. And then once I have my data in x and y, then I say that I want to plot x, y, and specify a specific type of plot. And then I also say that I want my plot to be blue, or the points and the line, I want them to be blue, and that we can see here. And then I say that I want the main title of the plot to be y is equal to x squared. So as you can see, it is quite easy to make a plot that looks nice in R. R has many built-in capabilities for doing statistics. So in this simple example, I'm generating 1000 values from a normal distribution with mean value 10 and standard deviation 3. These 1000 values, I store them in the variable data. Once I have my simulated data, I can create a histogram, which I do by this code here, and the result of the histogram, you can see that here. From the simulated data, I then create a 95% confidence interval with this code here. So this was just a simple example to demonstrate that you can do statistics in R quite easily, and there are many more capabilities that you can check out for yourself. In this example, I'm creating a linear regression model where my y variable is miles per gallon and my x variables are horsepower and weight. These three variables, they are found from the dataset empty cars. You can also notice that I'm using the tilde operator, and in R the tilde operator is used to separate the left and right hand sides in a model formula. So my left hand side, the y variable, is miles per gallon, and my right hand side, the x variables are horsepower and weight. So once I have fitted my linear regression model, I can make a summary of it. So with this code here, we get this result. So if you know about linear regression, for instance, you can see the coefficient estimates, the standard errors, the t-values, and the p-values. We can, for instance, also see the adjusted r-squared. So this was a simple example on linear regression. You can also do more sophisticated things, such as generalized linear models, and so on. So if you're interested in that, I encourage you to check it out. Tidyverse is a group of packages designed for data science and is highly popular. Tidyverse can be considered a dialect of the R language, and some of the core Tidyverse packages are Tibble, which provides a development of the data frame, dplyr, which is used for data manipulation, and ggplot, which is used for creating graphics and plots. Tidyr provides functionality to get tidy data, but tidyr will not be covered in this course. However, we're going to talk about Tibble, dplyr, and ggplot2. If you would like to check out the official website of Tidyverse, you can do so at this link. Tibbles are data frames, but they tweak some older behaviors. For example, if you try to access a column that does not exist in a data frame, you only get the value null. If you do the same in a tibble, you get the value null and a warning message. Tibbles are one of the unifying features of the Tidyverse, and you can also transform a data frame to a tibble by using the function as_tibble and then providing the name of the data frame that you want to transform. Turning a tibble back to a data frame can be done by using the function as_dataframe and then providing the name of the tibble that you want to transform. To learn more about Tibble, you can check out their official website or run the code vignette Tibble in R. dplyr provides a consistent set of verbs with which you can handle data frames or tibbles in an intuitive and user-friendly way. The use case for dplyr is that you can transform a dataset so that you can do the particular analysis or visualization that you want. So with this said, we have given a short background of dplyr and we are ready to dive into its powerful verbs. dplyr provides powerful verbs for handling single tables. We can group the verbs in 3 different groups depending on if they work with rows, columns, or group of rows. For rows, some examples include filter and arrange. For columns, some examples include select, rename, and mutate. For groups of rows, one example includes summarize. So in the next slide, we have a dataset called Star Wars, and from that dataset, we want to choose all the rows where the column skin color has the value light and the column eye color has the value brown. So as you can see, this code is quite elegant, and if you would like to do exactly the same thing or extract the same data without using dplyr, you will basically have to write this code here. In this slide, you can also notice that we use the pipe operator, and we're going to talk about that in the next slide. The pipe operator, denoted in this way, is used to chain multiple operations together. The output from one function is the input to the next, and the pipe operator is read as then. The pipe operator allows us to write a sequence of operations without having to do intermediate steps. So in this example here, we save the results in intermediate variables A1, A2, and A3. We could do, or rather we could achieve the same thing by using the pipe operator as we do here. And if we use the pipe operator, we have no need to save the intermediate results in variables. So the pipe operator is a very, very powerful concept, making your code more elegant and clean. In reality, we often work with multiple tables. One common thing to do is to combine columns from multiple tables into one. So in dplyr, there are 3 families of verbs that work with 2 tables at a time. We have mutating joins, which add new variables to one table from matching rows in another. So examples include inner join, left join, and full join. We have filtering joins, which filter observations from one table based on whether or not they match an observation in the other table. Some examples include semi-join and anti-join. And then we have set operations, which combine the observations in the data sets as if they were set elements. So some examples include union, intersection, and set diff. So in the next slide we have some examples. So here we do a left join, here we do a semi-join, and here we use the intersect function, or rather the intersect verb. So as you can see, using, for example, left join, semi-joins, or intersect is straightforward in dplyr. If you would like to check out the home page of dplyr, you can do so at this link. If you would like to learn more about one-table verbs, then you can, for instance, check this link here. If you would like to learn more about two-table verbs, then you can, for instance, check this link. ggplot2 is a data visualization package that is based on the book The Grammar of Graphics by Leland Wilkinson. The grammar of graphics is based on the insight that you can uniquely describe any plot as a combination of a dataset, a geom, a set of mappings, a stat, a position adjustment, a coordinate system, and a faceting scheme. To make a plot, we need a data layer, a geometric layer, and an aesthetic layer. The rest is not required and often has sensible defaults. In this example, we have created a scatter plot by using ggplot2. So in this code, we have a data layer and a geometric layer, and this code produces this scatter plot. If you would like to check out the home page of ggplot2, you can do so at this link. If you would like to learn more about ggplot2, then you can, for instance, check out this link here. At the top of all R scripts, installation and loading of packages should be done. So in my case, I have already installed these packages from before, so the only thing I need to do is to load the packages. So we run this code to load the three packages ggplot, dplyr, and readxl. These packages will be used later down in the script. To see which packages are installed, I can run this function library. And then we see the packages that are installed, and for example we see dplyr is one of them. If I continue to the code again, then I can also see which packages are currently loaded by running the search function. So I run this code, and we see that, for example, we have loaded dplyr, and we have also loaded ggplot2. The first program that we're going to run is hello world. So to do that in R is easy. We simply type print and then hello world. So I run this code, and we see here in the console that we have printed out the message hello world. The standard approach to assign a value to a variable in R is to use leftward assignment. So if I run this code and then print out the value of variable 1, then we see that it has the value leftward assignment. We can also do rightward assignment, and we could, if we want to, use an equal sign to assign a value to a variable, but that does not follow the standard. So that's not the preferred way to do it. If we would like to print out all the variables in workspace, we could use this function ls. So I run this code, and then we see that we have three variables in the workspace: variable 1, variable 2, and variable 3. These three variables, we can also see that in the environment. So they are also available here. If you want to read the documentation about a function, you can either write a question mark and the function name, or you could use the help function. So it's the same thing. So if I run this code, then we see the documentation for the ls function. If you want to delete a variable, you can do that by using the addm function. So I run this code and then print out all the variables in the workspace again. And then we see that variable 1 has disappeared. If you would like to delete all the variables in workspace, you can do it by this code here. So I run this code and then print out all the variables, and we see that there are no more variables in the workspace. Now we are going to look at data structures, and we are going to begin with vectors. So by using the concatenate function, I'm creating a vector and then assigning it to the variable v1. So I run this code and then I check, is v1 a vector? So I expect to get the answer true. So I run this code and we get the answer true, just as expected. If we would like to access elements from a vector, we can do that. So this code will access the fourth element, and this code will access the third and the seventh element. If I use a minus sign here in the indexing, then we will access all the elements except the third. So this code will access all the elements except the third, meaning that we expect to get 1, 3, and then 5 is not included. So you get 1, 3, 7, 9, 11, and 13. I run this code and we see that we did not get the 5, just as expected. Here we're going to access all the elements that are greater than 7. So I run this code and I expect to get the answer 9, 11, and 13. So I run the code and we got the answer 9, 11, and 13. Now I'm creating a new vector called v2 and then I'm printing it out. Now I am modifying elements. So I say that the first element in v2 should be equal to 1422. So I run this code and then print out the vector, and we see that the first element has been replaced. This code will replace all the elements that are greater than 1000 by 2222. So if I run this code and then print out the vector, we see that the elements that were greater than 1000 were replaced by 2222. And then this last line, 85 and 86, this will modify the vector in the sense that we will only keep the first and fifth element. So we're going to keep the first element, which is 2222, and then we will also keep the fifth element, which is 98. So I run this code and we see that we have only kept 2 elements. So we have covered vectors, and next in line are arrays, matrices, factors, lists, and data frames. I have provided quite a lot of example code that I encourage you to look through to really understand this. So to not make this video too long, I'm simply going to run through the code, and then, as I said, I really encourage you to look through this yourself. So now I will only run the code. Now we're going to look at operators, and we are starting with arithmetic operators. So the first thing I do is that I create two vectors, vector 1 and vector 2. And then you can see that I'm using the cat function, and what that does is that it concatenates the arguments and then prints them out. So I run this line and we will see addition of vectors. So 4 plus 2 is 6, 1 plus 2 is 3. So we expect to get the answer 6 and 3. Running the line, we get the answer 6 and 3. Then I do subtraction, multiplication, division, modulo, and then using the power operator. So that was arithmetic operators, and in the next video we're going to look at relational operators. Now we're going to look at relational operators, and the first thing I do is to create two vectors, vector 1 and vector 2. In this first example, we are checking if vector 1 is less than vector 2. And we see that 0 is less than 2 and 2 is less than 3. So we expect to get the answer true and true. So if I run this code, we see that we got the answer true and true just as expected. Then I'm using the less than or equal to operator, greater than operator, and then greater than or equal to operator, and then finally not equal to operator. So this was relational operators, and in the next video we're going to look at logical operators. Now we're going to look at logical operators, and I create two vectors, vector 1 and vector 2. Before we look at the operators, I'm doing a little remark here. So non-zero values in R are considered true. 0 is considered false. So if we run this code 10 and 4.3, then 10 is non-zero, meaning it is considered true, and 4.3 is also non-zero, meaning it is considered true. So true and true returns true. So running this code, we get true. Here we have 2.5, which is considered true, and 0, which is considered false. So true and false returns false. Running this code, we get the answer false. Okay, so here I'm doing element-wise AND. So I run this code, and we get true, false, false. And why is that? Well, true and true is true. True and false is false, and false and true is false. So you get true, false, and false. Here I'm using element-wise OR, and then I'm doing a logical AND and a logical OR. And you can notice that here, for instance, I'm using 1 ampersand, and here I'm using 2 ampersand. So if you want to check the details about the difference about that, then I have provided you with a link here to Stack Overflow. And then the final operation I'm doing here is negation. So if I run this code, not vector 2, then I expect to get the answer false, true, false. So I get the opposite. So I run this code and we get false, true, and false. Now we're going to look at an example related to conditional logic. So if we run this code, what answer do we expect to get? I claim that we expect to get the answer median, and the reason is that the variable x has the value 15 assigned to it. And because 15 is between 10 and 20, more specifically 15 is greater than or equal to 10, and it is also smaller than or equal to 20, then we will print out the message median. So if I run this code, we see that just as expected, we got the answer median. R has several built-in functions. So first I want to demonstrate some mathematical functions, and to do that I create a vector called numbers and assign it the values 1 to 4. So I create this vector, print out the numbers, and we see that we have the values 1, 2, 3, and 4. Okay, so first I calculate the sum, then I calculate the maximum, the minimum, the mean, the median, the range, and the range simply returns the minimum and maximum of the vector. So the range returns the minimum and the maximum of the vector, which is 1 and 4. And then I'm using the exponential function, the logarithm function, and then the square root function. R also has string functions. So here I'm creating a string, then printing it out, and it says programming is great fun, and I totally agree with that. And here I'm using substring, which basically extracts the letters that I want to extract. So I'm extracting the letters starting at index 1 and stopping at index 11. So we see that the first letter is P, and then if we stop at letter 11, then we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So when I run this code, I expect to get the answer programming. So I run the code, and we got the answer programming. ToUpper converts the string to uppercase. So it says programming is great fun, and everything in uppercase. And ToLower converts the string to lowercase. So I run this code, and we see that we get the message programming is great fun in lowercase. And then number of characters simply returns the number of characters in the string. And we get the answer 24. Creating user-defined functions in R is easy. So in this case, I'm creating a function called check even or odd, and this function takes one argument, x. And what the function does is that it checks if x divided by 2 has a reminder 0, then return the message even, else return the message odd. So if I run this code to create the function, and then use the function check even or odd with the argument 4, then I expect to get the answer even, because 4 divided by 2 has the reminder 0. So I run this code, and we get the answer even, just as expected. If I run the function check even or odd with the argument 3, I expect to get the answer odd, because 3 divided by 2 has a reminder 1. So I run this code, and we see that we got the answer odd, just as expected. Next, I'm going to create a function called rectangleInfo, and it will return two outputs. So first we calculate the area, then we calculate the perimeter, and then we create a named list containing the area and the perimeter. So if I run this function to create it, and then run the function rectangleInfo with the arguments 2 and 2, then we see that we got two outputs. And here I'm calling the function, but by using the default value for width. So we see that width has a default value. So I run this line, and once again we got two answers. So the area is 20 because 5 multiplied by 4 is 20, and the perimeter is 18 because 2 times 5 plus 4 is 2 times 9, and 2 times 9 is 18. And then here I'm calling the function with keyword arguments and then having width as my first argument. So I run this line, and once again we get two answers. So this was a function with multiple outputs. Now we're going to demonstrate looping or iterating. So in the first example, we write for I in 1 to 10 print I. So running this code, we expect to get the numbers 1 to 10 printed out individually. And looking at the console, that is exactly what we got. In the next example, I create a list called languages. And this list contains different strings. And in this case, each string is a programming language. So for example, R, Python, MATLAB, and so on. And then I write for language in languages print language. So running this code, we get each language printed out separately. You can also notice that the indexing variable I used is called language in this case. I could call it something else, so if I write I here and then print I, we will get the same output. So I run this code and we got the same output. And then finally I'm doing a while loop. More specifically, first I'm creating a variable I that has the value 0 assigned to it. And then I write while I is less than 4, print I. And then for each iteration I increment I by 1. So running this while loop, I expect to get the number 0 to 3 printed out. And that is exactly what we got. In this example, I'm going to demonstrate how you can store values from a for loop, and I'm also going to measure the two approaches that I'm going to show. More specifically, I'm going to measure the time it takes, and from that we can learn something in terms of which approach is more effective. So that is called benchmarking. So in this first approach, I create an empty vector, and then for each iteration, I create a variable result that I append to my vector. So running this code, this will take a while to finish, and we can see that the code is running because there is a stop sign here. So while that code is running, let's look at the second approach. So in the second approach, we have pre-allocated a vector, and this vector, my storage, contains 100,000 zeros. And then for each iteration, once again, we have a result, and we are replacing the elements in the pre-allocated vector my storage with the result. So if I run this code, we immediately get the results, or it immediately runs, so we don't see any stop sign, meaning it is done. And then in this case, or in both of the cases, I used system.time to measure how much time each approach took. So what I can do now is that I can print out time 1, and we see that it took around 25 seconds. And if I printed out time 2, then we see that it took basically 0 seconds. So the conclusion we can take from this simple experiment is that when possible, pre-allocate a vector if you're going to store the values. Because when you pre-allocate a vector, it is much faster than appending an empty vector. So this was a simple example on how you can measure how much time your code takes to run. You can load different type of data formats into R, and in this example I'm going to demonstrate how you can load in Excel data. So the first thing I'm doing is that I create a variable called file path and specify the file path where I have my Excel file. And then next I'm using the read Excel function, and then the argument I provide is file path. So I run this code, and then I'm printing out the first observations from my data, which is the read in Excel data. So I print out the first observations, and those we can see here. And then just for the sake of it, I'm creating a box plot of the data I loaded. So I run this code and we see a box plot. Now we're going to look at some of the plotting capabilities of R. And in order to demonstrate plotting, I'm going to use some, or more specifically, I'm going to use one built-in dataset in R. So to first check the built-in datasets, we can run the data function. And here we can see built-in datasets. And the dataset I'm going to use is called empty cars. So to load it, we simply write data and empty cars. So I run this line, and we have then loaded the empty cars dataset. Before I start plotting some of its variables, it's good to get a feeling for the dataset. So the first thing we can do is to read the documentation about it. So I type empty cars and running this code. Then we can read the documentation about the dataset. Next we can check the next we can check the dimensions of the dataset. So we can check the dimensions of the dataset. So I run this line and we see that it has 32 rows, 11 columns. Then I print out the first rows and we see how it looks like. And then I'm creating a summary of the dataset. And you can see that we got a quite nice summary. Next, I'm going to create a scatter plot of miles per gallon and horsepower. So I'm creating a scatter plot, and here I'm extracting the horsepower and miles per gallon variables. I specify a main title, specify labels for x-axis and y-axis. So I run this code and we see that we got a nice scatter plot. Here I'm creating a scatter plot matrix of 4 variables, and for that I'm using the pairs function. So I run this code and we see that we got a scatter plot of the 4 variables. And then finally I'm generating some data, x and y, so that I can make a line plot of it. So I run this code and we see that we got a line plot. So this was a short introduction to some of the plotting capabilities of R. R has many capabilities of doing different things related to statistics, and in this video we're just going to show some of the things that you can do. So the first thing we're doing is that we are setting a seed, and the reason why I do this is to get the results that are reproducible. So we want to get results that are reproducible, meaning that when you run the code on your computer, you will get the same results as I do. So that is why we are setting the seed. So I run this code, and next I'm simulating data from a normal distribution. So I run that code, and to visualize the data that I simulated, I'm making a histogram. And the histogram, we can see that here, and looking at the shape of it, it kind of looks, or it definitely looks like a normal distribution. This characteristic bell-shaped curve. And then I'm estimating the mean, standard deviation, and then calculating the number of elements in our data vector. So I run that code. And the reason why I did this is because I'm going to use it later. So I will show you that in a moment. Okay, next we calculate a 95% confidence interval. So running this code, we got a 95% confidence interval. And here on line 472, I'm calculating a confidence interval by doing it manually by using a well-known formula. So if you know some statistics, maybe you have seen this formula, but if you haven't, then don't worry, just skip it. But when I run these 2 lines, I expect to get the same answer because I'm calculating the confidence interval manually, and here I used a built-in function. So I run this code and we see that we get exactly the same results. So this was a short demonstration of some of the things you can do in R related to statistics. In this example, I am going to demonstrate linear regression. So the dataset that we're going to use is empty cars. So running the function head empty cars, we see the first rows of the dataset. Next, I am fitting a linear regression model where my y variable is miles per gallon and my x variables are horsepower and weight. These 3 variables are found in the dataset empty cars. So fitting my model and then running linreg, we can see the coefficients if we want that. If we would like a more complete summary, we can write summary and then linreg. So I run this code and we see that we get a more complete summary of the model. So for example, we see coefficient estimates, standard errors, t-values, p-values, and for example, adjusted r-squared. The final thing that I'm going to demonstrate is that we can calculate a confidence interval for the estimated parameters. So we use the function confint and then our model linreg. So confint linreg, and running this code, we see that we got a confidence interval for our estimated parameters. Now we're going to look at single table verbs from dplyr. The data set that we're going to use is called Star Wars. So running the code $Star Wars, we can see the documentation about the data set. So here is the documentation. And we can check the dimensions of the data set, and we see that it has 87 rows and 14 columns. We can also print out the first rows of the data set to see how it looks like, and we see that here. Next, I'm going to choose rows based on specific column values. More specifically, I'm going to choose the rows where the column skin color has the value light and the column eye color has the value brown. So running this code, we see that the column skin color has the value light and the column eye color has the value brown, just as we specified. We could do the same thing without using dplyr, and then the code would look like this. So running this code, we get the same results. If we want to, we can order the rows with the highest height first. So I run this code, and we see that the height column is ordered in descending order. So 264 is bigger than 234, which is bigger than 229, and so on. Next, we can create two new columns, height M and BMI. And we're also going to place those two columns first. So we can see here that we're using two pipe operators. So if I run this code, we see that we have created two new columns, height M and BMI. And then the final example we're going to look at is that we can calculate the mean height and mean mass for each unique group of species and sex. So if I run this code, we see that we get the mean height and mean mass for each unique group of species and sex. So that was an example on single table verbs from dplyr. Dplyr also has verbs for two tables. And now I will basically just run through the code, and you are encouraged to look at the details yourselves. So the first thing I do is that I create some data for demonstrating mutating joins. So I create the data. Then I'm doing a left join, an inner join, and a full join. Okay, next we go to filtering joins. And once again, I'm creating some data to demonstrate filtering joins. And then we can do a semi-join. We can also do an anti-join. And finally, I'm creating some data to demonstrate set operations. So I am creating the data. And then we can do intersect, union, and setdiff. So look through the code for two table verbs because it can be very useful in your data analysis. Now we're going to look at plotting with ggplot2. The dataset that we're going to use is called MPG. So running the code $MPG, we can look at the documentation. Next, we print out the dimensions of the dataset, and we see that it has 234 rows and 11 columns. Next, we print out the first rows, and we see that the dataset looks like this. And then finally, we do a summary of the dataset. Okay, so in the first example, we're creating a simple scatter plot. And we can see the plot here. Next, we're going to color the points according to which class the car belongs to. So running this code, we see that there are different colors depending on which class a car belongs to. In the next example, we're making a separate scatter plot depending on which class the car belongs to. So now we're creating a separate scatter plot. So running this code, we see that we have separate scatter plots. And then in this example, we're going to display multiple geometric layers. So if I run the code, you will see what happens. So you see here that we have, in this case, 2 geometric layers. And finally, I'm going to create a horizontal box plot by switching the X and Y axis. So running this code, we see that we got an horizontal, or more specifically, we got several horizontal box plots. So that was a short demonstration of plotting with ggplot2. Okay, so we have now come to the end of this course in R programming. If you liked the video, then you can like it. And if you would like to see more content in the future, you can subscribe to the channel. So with that said, I would like to thank you for watching and wish you good luck with your R programming. Bye.